what, November 16th? All right, we're going to verify that. Let me get this out of here now. We're going to verify that 1 minus tangent squared of x over 2. Uh-oh. We have a Webwork question. Okay, I'll get to that next. All right, right now we're doing verify that 1 minus tangent squared of x over 2 is 2 cosine x over 1 plus cosine x. So what I like you to do when you verify identities is tell me what side you're starting with, and then start making replacements using known identities. So I'm going to start with the left-hand side. You'll be giving the list of identities. So here are the ones you'll be given. And I see several versions of the tangent of half of an angle. The one that looks most like what my answer looks like on this particular exercise is the middle one. So I'm going to replace tangent of x over 2 with the sine of x over 1 plus the cosine of x. Now this tangent is squared, so all of that is squared. So here I'm using the fact that the tangent of a divided by 2 is the sine of a over 1 plus the cosine of a. Take that out of my way. Now when I square that, it's going to give me the square of the top divided by the square of the bottom. So I'm going to write that as sine squared of x over 1 plus the cosine of x, all squared. I got to do some subtraction, but in order to subtract, I have to have a common denominator. So treat this as 1 over 1. The common denominator is the 1 plus cosine of x squared. So let's rewrite the 1 over 1 as 1 plus cosine of x squared over 1 plus cosine of x squared. So here we're just getting a common denominator. Now that we have a common denominator, we can make one fraction out of that. So I can just list the common denominator once, and then put that stuff back on top. So I'm getting kind of close. I guess I have to do the actual squaring. So let's take 1 plus cosine of x and multiply it with itself. I'll keep the bottom intact. I won't multiply that out, because I'm hoping something will cancel further down the line. So we do this multiplication as per usual. 1 times 1 gives me 1. 1 times cosine of x gives me plus cosine of x. Now the other term, plus cosine of x times 1 gives me another plus cosine of x. And then finally multiply two cosines together, so I get plus cosine squared of x. These two are like terms, so I can add them and get two of them. What I have, what I'm trying to work towards, doesn't have any signs in it. So at this stage in the game, I'm going to replace sine squared with 1 minus cosine squared. That's the Pythagorean identity. So I'm going to put these two together, and I'm going to put a 1 minus cosine squared back here. So I have 1 plus 2 cosine of x plus cosine squared of x minus, now I'm going to put that in parentheses, 1 minus cosine squared of x. In the next step, I'm going to take those parentheses off and distribute this minus sign through those two terms. And so we have 1 plus 2 cosine of x plus cosine squared of x minus 1 plus cosine squared of x all over this. So now I have these two. I've got a 1 minus 1, so those are gone. And then I have a cosine squared plus a cosine squared, so I get two of those. So we have 2 cosine squared of x. Then I still have plus 2 cosine of x all over this denominator. And you can't see that. Those two terms have common factors of 2 and cosine of x. So I'm going to factor out the greatest common factor. So when I pull that out of here, I've got one of the cosines left. Plus, when I pull it out of here, I just have a 1. So we're just about there. 1 plus cosine of x is the same as cosine of x plus 1. So I have a common factor on the top with on bottom. I'll cancel one of them, and then we've got it. That cancels with one of those, and we have this written as 2 cosine of x divided by 1 plus the cosine of x. Okay. Bit on the old long side, eh? So again, when you're verifying identities, you typically start with the identity that looks like something that you can expand. When you expand it, then it opens up a bunch of algebra. So I didn't do anything fancy here. I just did the actual getting common denominators, factoring and canceling, stuff like that. Yes, 5 on the review as well. Don't worry, I'll get back to the web work. So I got it. My stuff. Come on back here. Where'd it go? So this one here, cosine of x is -7/25. cosine of theta, sorry, cosine of theta is negative 7/25. Theta is in quadrant 3. And sine of alpha is negative 3/5. And alpha is in quadrant 4. Find the sine of theta plus alpha, sine of theta, a tangent of theta minus alpha. All right. Given cosine of theta is negative 7/25, theta is in quadrant 3. Sine of alpha is negative 3/5, alpha is in quadrant 4. Find those two things. You know what to do? Given an expression, expand it with the identity, use right triangle trigonometry to fill in the pieces of that identity. Yes? Okay, so the sum of two angles is the sine of the first angle, cosine of the second angle, plus the cosine of the first angle, sine of the second angle. That's the identity. Again, you're given that one, you can look it up. Then I'm going to go and draw a right triangle here. First, a right triangle in quadrant 3, theta, in which the adjacent over the hypotenuse will give me negative 7/25. Then we have to find this length here so that I can get the sine of angle theta. So let me do that right in here. This says that b squared plus negative 7 squared is 25 squared. 25 squared is 625. So b squared, take 49 away from that, is 576. B is going to be the square root of 576. And I think that is, oh, I know that one, 24. B is going down, so I'm going to take negative 24. Then I'm going to do the same thing with alpha. I'm going to draw a quadrant 4 triangle for angle alpha. The sine gives me the opposite over the hypotenuse, and that was a 3, 4, 5 triangle. So that other side's a positive 4. So sine of angle theta is found by going to the triangle here. The sine is opposite over hypotenuse. So I'm going to put in negative 24/25 right here. Cosine of angle alpha, go to this triangle and use the adjacent over the hypotenuse. So cosine of angle alpha is 4/5. Cosine of angle theta is given. That was the negative 7/25. Sine of angle alpha was given as negative 3/5. So we simplify here. 4 times 4 is 16. 8, that gives me a 96, and it's negative. And that's going to be two negatives multiplied together to give me a positive 21. 5 times 25 is 125. Negative 96 plus 21 is a negative 75. You want to reduce, you may. The tangent of A minus B identity is the tangent of the first angle minus the tangent of the second angle divided by 1 plus the tangent of the product, tangent of theta, tangent of alpha. You get those numbers from the triangles. Tangent of theta, we go up here to this triangle. Tangent is opposite over adjacent. So the tangent of theta is negative 24 over negative 7. Get the tangent of alpha here, opposite over adjacent is negative 3 over 4. All right, these two negatives cancel and make me a positive. So I've got a positive 24 over 7. There's a positive 24 over 7. I've got 24 over 7. Two minuses will tell me to add that with 3/4. On the bottom, we have 1. Well, that's going to be a negative times a positive will be a negative. 4 times 7 is 28. 3 times 24. 72. You can stop anytime, but I'll keep going to get the answer in the note. I'm going to get a common denominator both on the top and the bottom. So the common denominator is going to be 28 everywhere. We'll multiply that by 4 over 4, that by 7 over 7, that by 28 over 28. So that's going to be over 28. 4 times 24. 4 times 4 is 16. That's 96 plus 21. Down here I have 28 minus 72 over 28. 96 plus 21 is 117. 28 minus 72 is a negative 44 maybe. And the 28s will cancel. And so our answer is 117 over negative 44. I put it away. What does the review key say? Probably. Did I do anything wrong up here? Yeah, there are several mistakes on that key. I try to correct them, but I don't always. Yes. Okay. Any questions on this one? Yeah, check my arithmetic. I don't know where the 117 is coming from. Okay. Number 8. Write a single trig function equivalent to the sine squared of 2 pi over 5 minus the cosine squared of 2 pi over 5. A single trig function equivalent to that one. So I'm going to put up my identities here. We're going to hunt for one that looks the most like that. The only one I see that's got the difference of squares in it is this one, but it's written backwards. I've got sine squared minus cosine squared, and this one has cosine squared minus sine squared. Well, I can fix that. I can say that sine squared minus cosine squared is the same as -1 times cosine squared minus sine squared. And now it looks like that identity under there. Now it looks like this one. So the difference between the sine and cosine squared of a single angle can be written as just the cosine of twice that angle. So now inside the parentheses, I'm going to have the cosine of twice that angle. Better? And so when I double that angle, I get 4 pi over 5. And I believe on the answer key, I left off the minus sign. So it's supposed to be there. Okay. Yes, sir.
Can you explain how is that you when it's switched around cosine and sine again? You have the old sine for
If I multiply something by -1, doesn't it change the sign?
Yeah.
So if I want a minus sign here, there it is. If I want a plus sign here, there it is. So if I change the order in which a subtraction is written, I'm essentially factoring out a -1. Right? A minus B is the same as minus B minus A. Okay? Just a little algebra, right? Here I'm using the fact that if I subtract that way, it's the same thing as turning it the other way. Turn it the other way. Fun with numbers. Okay. Right? If you subtract 2 minus 5, you get a -3. But if you subtract 5 minus 2, you get a +3. You get the same number, but opposite in sign. That's what I'm doing here. Yes. The instructions on this one are to simplify. So simplify typically means write in terms of sines and cosines and see what happens. Several ways you can do this. Probably the obvious way is to say that secant is 1 over the cosine, so secant squared is 1 over the cosine squared. Cosecant is 1 over the sine. So I'm going to write those in terms of sine and cosine. So this becomes 1 over the cosine squared. Then I subtract that 1. This is 1 over sine squared. And then I subtract that 1. But when you subtract, you need a common denominator. So up here on top, I'm going to think of this as cosine squared over cosine squared. And on the bottom, I'm going to think of this as sine squared over sine squared. So I keep this 1 minus cosine squared minus cosine squared over cosine squared. And then on the bottom, 1 over sine squared minus sine squared over sine squared. Got to get a common denominator to subtract. Once you get the common denominator, you can write them as a single fraction. So on top, I'll put it all over cosine squared. And above that, I'll have 1 minus cosine squared. Let's do the same thing down here. Here's the sine squared. That's the common denominator. On top, I'm going to have 1 minus sine squared. Does anybody know what 1 minus cosine squared is equal to? That is equal to sine squared. What about 1 minus sine squared? So 1 minus cosine squared is sine squared. 1 minus sine squared is cosine squared. So all I did is I replaced this with sine squared. I replaced this with cosine squared. So now I've got one fraction divided by another. We take the one that's on the bottom, flip it over, and multiply. And so we get sine to the fourth over cosine to the fourth. What trig function is sine over cosine? So you can also write that as the single trig function tangent to the fourth of theta. Is that okay?
Is secant squared, like one tangent squared?
Secant squared minus 1 is tangent squared, and cosecant squared minus 1 is cotangent squared. So you could have gone about it much quicker that way. Yes. I'm sorry, which one? D? 2D? What's that? 2D multiply sine of theta minus cosine of theta. Cosecant plus secant. The instructions are the same, simplify. And so typically, again, that means write in terms of sines and cosines and see what happens. So before I multiply this out, I'm going to write cosecant of theta as 1 over the sine of theta. I'm going to write secant of theta as 1 over the cosine of theta. And now we're going to multiply it out. I'm going to take the sine of theta and multiply it with both of those. Then I'm going to take minus the cosine of theta and multiply it with both of those. So first, sine of theta times 1 over sine of theta gives me sine of theta over the sine of theta. Sine of theta times 1 over cosine of theta gives me sine theta over cosine theta. Now it's time for cosine's turn. Minus cosine times 1 over sine gives me minus cosine over sine. Minus cosine times 1 over cosine gives me minus cosine over cosine. The fraction in the front and the fraction in the back, what are these two equal to? Those are ones. So where I come from, 1 minus 1 is 0. We can get rid of those. What we have left is the subtraction of two fractions. That can only be done if they have a common denominator. The common denominator is cosine times sine. So I'm going to multiply this first fraction by the cosine over the cosine. Oops, sorry, sine over the sine. Let's take that away and go to the next line. Times the sine of theta over the sine of theta. I'm going to multiply the second fraction by cosine over cosine. And now they have the same denominator. Next page, I'm going to quit being blurry. I'm going to write this as 1 fraction over sine times cosine. So I'm going to have the sine. Sine times sine gives me sine squared. Cosine times cosine gives me cosine squared. How far we need to go with this. What am I trying to get to? Let me see what I got left. Tangent minus cotangent. Okay. I can do that. Maybe. Come on back. Where'd it go? There it is. Okay. So I'm going to break it up again. I'm going to say this is one fraction. And then minus the other fraction. What did I could have stopped several steps ago, huh? I could have stopped several steps ago. I'm just taking me back. All right, one of these cancels with that. One of these cancels with that. I have the sine of theta over cosine theta. I had that on the previous page. That one is the tangent, and that one is the cotangent. I could have done that right back here. I could have skipped the getting the common denominator step. So I will. I'll just cross that out. Draw me an arrow up here and say I'm done. Then I'll throw this page away. Back up higher. Press. Yeah, I still have that one to do. Are we still doing this? Yes. 12. Let me get all the ones on the review sheet, and then I'll go do the web work. You guys tell me you don't want me to cover anything new today? Okay, let me remind you of the inverse trig functions. Remember that an inverse trig function is an angle. I'll come back to that in a second. Right? So in section 6.1, we defined the inverse trig functions. In terms of their reversing the order. If a function f takes this number to this, then its f inverse does it the other way. So when I take the sine of an angle and give you a number between 1 and -1, the inverse sine takes a number between 1 and -1 and gives you back the angle in the prescribed interval. The way as follows: we defined the inverse sine of a number. I guess I've been using an x, is an angle y if and only if the sine of that number y is that angle x. Where this number here are the numbers between 1 and -1. But the angles that it spits out are acute angles between -π/2 and π/2. So it's only given me angles back here or here. We define the inverse cosine the same way. The inverse cosine of a number x is an angle y if and only if the cosine of that angle y gives you back x. Still, those x's are between 1 and -1. But this time the y's are between 0 and pi. So the inverse cosine is looking for an angle that lives up here. And finally, we had the inverse tangent. of an angle x, of the number x is an angle y, if and only if, you guessed it, the tangent of that angle y gives you back x. The inverse tangent had an infinite numbers that we could put here. So x is between minus infinity and infinity. But the numbers y are like sine. They're between pi over 2 and negative pi over 2. Strictly this time, since the tangent of pi over 2 is not defined. So it gives you an acute angle there or there. We had an alternative way of writing those inverse trig functions. Another way of writing the inverse sine is to call it the arc sine. The inverse cosine is also known as the arc cosine, and the inverse tangent is the arc tangent. Those are used interchangeably even today. The other three inverse trig functions can be found using an identity that, for instance, the inverse secant of a number x is the same as the inverse cosine of the number 1 over x. So then I can go back and use that. The inverse cosecant of a number x is the same as the inverse sine of 1 over x. And then the inverse cotangent of a number x is the same as the inverse tangent of 1 over x. So that I don't have to memorize the ranges of those, I can just relate them back to those three. So if you're asked to find an inverse trig function of a number, you're looking for an angle. It might be an angle in the angles that we know and love, or it might be something that we use right triangle trigonometry to find. So let's go back and look at problem number 12 on the review sheet. Find values of each of the following. So let me just do them. Let me write them here and then I'll switch the camera. Arc tangent of square root of 3. The arc cosine of negative 1/2. The inverse sine of the sine of 5 pi over 6. And then finally the cosine of arctangent of 4/3 minus arccosine of 5/13. Okay. The first one, the arctangent of square root of 3 is an angle that I take the tangent of to get the square root of 3. It is an angle that I take the tangent of to get the square root of 3. It's one of the angles you know and love. Pi over 3, because tangent is sine over the cosine. Sine of pi over 3 is square root of 3 over 2. Cosine of pi over 3 is 1/2. That ratio does indeed simplify to the square root of 3. So that's our answer. That's knowing your trig functions.
How do we know that it's not the other value for the, okay,
Because the way we have to give our angles. For the tangent, if you've got a positive number, it's quadrant 1. If you got a negative number, it's an acute angle in quadrant 4. So it's minus the other one. So if I asked for the arctangent of negative radical 3, instead of saying that it's 5 pi thirds, which is in quadrant 4, it's negative pi thirds because it must be acute based on the definition. Okay, so that's why I draw these little pictures to help us remember. So when I'm looking for the arc cosine of negative 1/2, I am looking for an angle that I take the cosine of to get -1/2. Not just any angle. If it's going to be negative, it's going to be an angle in quadrant 2 because of the way we had to restrict the domain in order to define these inverse trig functions. So firstly, we just said that the cosine was 1/2 at pi-thirds. So where in quadrant 2 is my version of pi-thirds? 2 pi-thirds. So our cosine of -1/2 is 2 pi-thirds. And according to this identity up here, the arc cosine of -1/2 is the same as the inverse secant of 2. They take on the same value if you flip the thing over. So if I asked you for the inverse secant of 2, you say, well, that's the same as the inverse cosine of 1/2. The inverse cosine of 1/2 is pi/3. Okay, for the next one, the inverse sine of the sine of 5 pi/6. Typically, these two functions undo each other. That one undoes that rule, but it's not going to give you this back because the inverse sine is not defined in quadrant 2. The inverse sine is only defined in quadrant 1 and quadrant 4. So if I take this function and apply it to that, instead of getting 5 pi/6, 5 pi/6 is a second quadrant angle. Cosine, sine is positive in quadrant 2. This combination is going to project it back to quadrant 1 because of that. So the quadrant 1 version of 5 pi/6 is pi/6. All right, for the next one, 4/3 and 5/13 are none of the values in our set of reference angles. So instead of trying to find the exact angle, I'm going to write those as angles, and I'm going to find the cosine of the difference of those angles using right triangle trigonometry. So let me move that one to the next page. Cosine of the arc tangent of 4/3 minus the arc cosine of 5/13. Inverse trig functions are angles. We're looking for angles when we're given a trig function, their inverse trig function. So I'm going to call them angles. I'm going to call this one angle A, and I'm going to call this one angle B. Where angle A is the angle that is the arc tangent of 4/3. That means it's an angle that I take the tangent of to get 4/3. Angle B is the arc cosine of 5/13. So that means it's an angle that I take the cosine of to get 5/13. Both of those are positive numbers, so they both represent angles in quadrant 1. Tangent describes the opposite over the adjacent. That's a 3, 4, 5 triangle, so the hypotenuse is 5. For angle B, I have the adjacent over the hypotenuse. So do you recognize those two numbers? You know what the next one is? It's the 5, 12, 13 triangle. Now I'm going to rewrite this as the cosine of A minus B because I have an identity for that. I'm going to say that the cosine of A minus B is cosine A cosine B plus sine A sine B. one of the identities you'll be given. You can look that one up. Now I go to the picture for angle A. Cosine of this angle is 3/5, adjacent over hypotenuse. For the next one, I move over here. The cosine of that is 5/13. The sine of angle A is 4/5. And the sine of angle B is 12/13. 5 times 13 is 65. Both of these have a 65 on the bottom. So let's kind of shortcut it. 3 times 5 is 15. 4 times 12 is 48. 15 plus 48 is 63. Okay. Let me throw some more of those at you. Little practice. Find the, fill in the blanks. The inverse tangent of -1. The inverse sine of negative square root of 2/2. The inverse cosecant of -1. The inverse cosine of square root of 3/2. Says yourself. Tangent of what angle is -1? Sine of what angle is negative square root of 2/2? Cosecant of what angle is -1? Cosine of what angle is square root of 3/2? Those blanks must contain angles. For all of them, except for the cosine, they must be acute angles. For the cosine, that one is an acute angle because that's a positive number. So where's the tangent equal to +1? 45 degrees, pi/4. Right? So the tangent is -1 at negative pi/4. You got one? You got one? Negative pi/4. Where is the sine? What angle is the sine going to be square root of 2/2? Pi/4 again. So the sine is negative square root of 2/2 at negative pi/4. For the cosecant of what angle is -1? Well, it's the same place where, remember, the cosecant of -1 is the same as the inverse sine of 1/-1. But 1/-1 is still -1. So at what angle am I taking the sine of to get -1? Except for you have to go that way. Negative pi/2. What angle do we take the cosine of to get 3 square root of 3/2? Pi/6. What about the inverse cosine of negative square root of 3/2? And it's not negative pi/6 for the cosine, because for the inverse cosine, we have to spit out angles there. For the inverse sine and the inverse tangent, we go acute. For the inverse cosine, it's quadrant 1 or 2. So I need the quadrant 2 angle associated with pi/6. 5 pi/6. Okay. So remember when I told you trig is a memorizing game? Here it's the memorizing game gone backwards. Right? I give you the value, you give me the angle. That's what we're doing with inverse trig functions. Okay? All right, are we still on the review sheet? Yes. Okay, number 7 on the review sheet says, given the cosine of twice an angle, find both the sine and the cosine of the single angle. So this one is a little bit backwards. Usually we're given the single angle and asked to find the double angle. But we start the same way. We look up our identity for the cosine of twice the angle. And I'm going to try to use one of these 3 identities that only has one trig function in it. I don't want to try to use one that has 2. I want to try to cut back my work. So I'm going to go ahead and use this second one, that the cosine of twice an angle is 2 times the cosine squared of the single angle minus 1. So I'm going to start with the cosine of twice an angle is 2 times the cosine squared of the single angle minus 1. This is where we normally substitute in the drawing from the triangle, the cosine of the single angle. But we're looking for the cosine of the single angle. We have the number to put in on the left-hand side. So I'm going to fill that in for the expression on the left and solve the equation algebraically for the cosine of the angle. So the number on the left is equal to 7/8. Solve for the cosine of A. So the first thing I need to do is add 1 to both sides. But 7/8 plus 1 is 7/8 plus 8/8. I got to continue that on another page. Write that same step up here. I have 7/8 plus 1, but 1 is the same as 8/8. And on the left-hand side, I still have 2 cosine squared of A. Now I can add those 2 numbers and I'll get 15/8. I'm solving for the cosine, so let's divide by 2. Dividing by 2 is the same as multiplying by a half. So on the left-hand side, I have 15/16 is equal to the cosine squared of A. So the next step is to take square roots, but I don't know whether to take the positive square root or the negative square root. So I go back to the condition that was given initially. 2x is between 3 pi over 2 and 2 pi. I need to know where angle x is. So I'm going to take this equation and divide it by 2. Divide all three parts by 2. And when I simplify that, it says that 3 pi over 4 is less than or equal to x, which is less than or equal to pi. Can anybody tell me what quadrant that is? Where are all angles between 3 pi over 4 and pi? Agree? In quadrant 2, is the cosine going to be a positive number or a negative number? It's going to be a negative number because we're in quadrant 2. So I have that the cosine of A is negative square root of 15 over the square root of 16, but the square root of 16 is 4. Then once you know the cosine of A, you can draw a triangle in quadrant 2 and find the sine of A. So here's my quadrant 2. Here's my quadrant 2 triangle. Cosine is adjacent over the hypotenuse. And I need to find this number over here to get the sine. So b squared plus negative square root of 15 squared is 4 squared. Looks like b squared is 1. So b has to be 1. And in quadrant 2, b would be a positive 1 because that triangle is going up. Then I know the sine of angle A is opposite over hypotenuse. Okay? Yes? We can. Okay, I got a hint not to forget the question. All right, I'll do 16 and then I will do your Webwork question. I just feel like we've done all the Webwork questions. Haven't we? Haven't we done every single Webwork in class? All right, number 16 is solving a trig equation. We've got the product of a cosine with a cotangent equal to a cosine. And we want to give all angles theta one lap around the unit circle. Give all angles one lap around the unit circle. I said both in radians and in degrees, just so you get extra practice. Solving trig equations usually involves getting the trig function by itself and the number on the other side, or if you have several trig functions, getting a 0 on one side and factoring. So since I have several, I'm going to move that one over and try to factor. Okay, that's your plan when there's more than one trig function involved. If we have to get 0 on one side and can't factor, then we try an identity. But I think I'll be able to factor this. I'm going to subtract cosine of theta from both sides. Now I have two terms, both of them have a common factor of cosine of theta, so I factor it out. And what's left will be a cotangent of theta minus 1. Factoring makes it easy because when you have a product equal to 0, then each of the factors could possibly be 0. So I have two equations now to solve. Cosine of theta is 0, or the cotangent of theta minus 1 is 0. Can you tell me all angles, either in radians or degrees, at which the cosine is 0? Pi over 2 and 3 pi over 2. The next one, we're looking for angles at which the cotangent of theta is a positive 1. Cotangent is like tangent. It is positive in quadrants 1 and 3. The only time cotangent is 1 is when cosine and sine are the same. Pi over 4 is in quadrant 1. What's in quadrant 3? 5 pi over 4. So theta is pi over 4 and 5 pi over 4. And so if you want degrees, pi halves is 90 degrees. 3 pi halves is 270 degrees. Pi over 4 is 45 degrees. This is 90 degrees away, so that's 135 degrees. Okay, so that again is kind of that knowing your basic reference angles. But the trick is get the 0 on one side and then solve by factoring. I think so, right? That's 90 degrees away. Oh, I got to go further. I have to go 180 degrees away. 180 plus 45 is 225. Do I get partial credit? God, you greedy little. If you give a mouse a cookie, they want 10 more points. Okay, I promised I'd do this Webwork problem. Let's do this now. Given sine of alpha is equal to -8/9. Alpha is in which quadrant here between pi and 3π/2? Which quadrant is that? That's quadrant 3. Find the sine of alpha over 2. So if we're looking for the sine of a different angle than the one we're given, we have to use an identity. The identity for the sine of alpha over 2 is going to be plus or minus the square root of 1 minus cosine of the single angle over 2. And so now we fill the numbers in. How do we fill the numbers in? Well, we know one of them. We should know them all. We draw a triangle. We draw a triangle in quadrant 3. For angle alpha, sine is opposite over the hypotenuse. In quadrant 3, the adjacent side is also going to be negative, but let's find it. X squared plus -8 squared is 9 squared. Eight squared is 64, 9 squared is 81. 81 minus 64 is 17. So X is going to be, like I said, negative square root of 17. So the cosine of that angle alpha is adjacent over hypotenuse. Now we're going to decide which of these two signs to keep out front by looking here. If I know where angle alpha lives, I can find where angle alpha over 2 lives by dividing everything by 2. If I divide that by 2, divide that by 2, and divide that by 2, I have that alpha over 2 lives between pi halves and 3π/4. What quadrant is that? Second quadrant. In the second quadrant, is the sign a positive or negative? So I'm going to take the positive. And so if you simplify that a little bit, I got 2 minus signs in there. Let me copy it down up here and go to my next page. I've got that the sine of alpha over 2 is equal to the square root of 1 minus negative square root of 17 over 9 over 2. I'm sorry. Yeah. Two minuses means I'm adding up there. I get the common denominator of 9 by writing this as 9 over 9. So I have the square root of 9 plus the square root of 17 over 9 divided by 2. I divide by 2 by multiplying by a half. And so I have the square root of 9 plus the square root of 17 over 18. Okay? Time for one more if you got one more on me. Yes. On the review. Right, cotangent of 42 in terms of an equivalent cofunction. So our cofunction identity, right? It tells you what it's a cofunction of. It's a cotangent. Functions are cofunctions of each other if they take on the same value 90 degrees away. So the cotangent of 42 degrees is the same as the tangent of the angle that's 90 degrees away from 42 degrees. Right? 92 minus 90 minus 42 is what, 48 degrees? Cotangent of 42 is the same as the tangent of 48. Same thing's true with sine and cosine. They take on the same value 90 degrees away from each other. Secant and cosecant take on the same value 90 degrees away from each other. Think of your right triangle trig. Here's the right angle. Here's, let's say that the angle's here. The cosine of that angle is adjacent over hypotenuse. The angle that's 90 degrees away from this one is up here, right? And the sine of that angle is that over that. They take on the same value of the complementary angles of a right triangle. That's what the cofunctions identities say. Are you going to do good on this test? I'm not going to make multiple choice this time because you guys just slap down answers and don't show work. Means it's going to be a which to grade, rhymes with which anyway. I've got short answer. You can put your steps in there. And I tried to make the short answer pretty dang short, so don't get inventive. A lot of it is memorized. Yes, sir. Now you can make your own unit circle. All right, I've got to wean you away from that. Just show up with your knowledge. I'll give you a test. You write your answers. And I'll give you the list of identities that I said I'd give you. The other ones I want you to know. I can't help you if you don't do the knowing part. Yes, sir.
I was